start it now. Recording. All right, everyone. Thank you so much for coming today. Today we're going to be reviewing again SN1, SN2, E1, and E2. I know that we keep talking about this topic, but it's a very fundamental concept in organic chemistry. And because there's so many different factors, it can actually be very difficult to apply like every single aspect of it to problems. So we'll be going over what we were talking about on Monday again, and we're going to be trying to apply it to some more complicated problems. So yeah, once again, the reason why this is so difficult is because they all have very similar starting products. So if you were working in a lab, you would have your acyl halide and like some Lewis base. You would leave it in your container with some solvent to dissolve everything, and you would leave it there for a couple of weeks or so. And when you come back, you need to understand like what kind of product you have. Is it going to be a substitution product? Is it going to be an elimination product? And is it going to be like enantiomically pure? Is it going to be one enantiomer or a bunch of enantiomers or like a mixture of different products? And so understanding all the different factors, you can be better at predicting what kind of product you were going to get. And so first of all, one of the major ways that you can predict the product is using the substrate. So we've already covered this. Does anyone remember what kind of reaction you're going to see if you see a primary acyl halide? Is this going to be SN1, E1, SN2, E2? Yeah, it's going to be SN1 and E1. You can see both these reactions. And also one thing to keep in mind is the presence of that beta hydrogen. If there's a beta hydrogen, then this can obviously, sorry, I spoke SN2, E2, sorry about that. SN2, E2, because there's not going to be that steric hindrance. And so one thing to keep in mind is that beta hydrogen. In order to do E2, you need that beta hydrogen. So if that's not present, you're not going to see any E2 products. You're only going to see SN2 products, no matter what other materials are present. And so another thing is tertiary acyl halides. If you see tertiary, what kind of products are you going to see? What kind of reaction are you going to see? Is this going to be SN1, E1, E2, or SN2 for tertiary?
SN1 or E1?
Yeah, exactly. And that's because the tertiary substrate is going to stabilize that carbocation intermediate. And then secondary acyl halides, what kind of reactions can you expect to see with this reaction, with this substrate? Yeah, all of them. You can't factor any of them out. You're going to have to look at all the other factors in the reaction in order to narrow down what reaction it's going to be. So this is one important thing to keep in mind. So remember, with primary acyl halides, the main issue is that there's no steric hindrance. And so because of that, you can do things like SN2. That's not going to be hindered at all. With tertiary acyl halides, what's going to happen is that it's going to stabilize that carbocation intermediate. So that's why it's going to favor SN1 on E1. Although another thing to keep in mind is that E2, it's not going to be as sterically hindered as SN2. So you could potentially see E2 reactions with tertiary acyl halides. Although you would normally, when you see this, you should mostly, the main factor you should think of is carbocation stabilization. And yeah, once again, with secondary acyl halides, there's nothing that you can cross out. You still have to consider all the other factors in order to figure out what's going on. So yeah. Next thing to keep in mind is solvent. So normally you will chiefly be contrasting polar protic solvents and polar aprotic solvents. Not to say that all the other types of solvents are important, it's just that these are, when you're considering solvents, these are the two types you're contrasting. So with polar protic solvents, if you remember, that's going to be a solvent where there's going to be an electronegative group connected to a hydrogen. And so because of that, that hydrogen can participate in hydrogen bonding. So hydrogen bonding occurs whenever possible. And so these hydrogen bonds chiefly interact with the nucleophile. And as you remember from Monday's lecture, they're going to surround that nucleophile and reduce its nucleophile strength. And so because of that, it's going to limit SN2 reactions. It's not going to limit E2 as much. It's going to actually favor that. And also, if you remember from Monday's lecture, it also favors SN1 and E1 because that product solvent is going to stabilize the carbocation formation. And then we can contrast this with polar aprotic solvents, where there's no hydrogen binding. These solvents could have hydrogens, they're just not connected to an electronegative group. And so they're not going to participate in hydrogen binding. They're not going to surround that nucleophile. And so because of that, these reactions won't favor SN1 E2. So SN1 and E1, there's a mistake in the slide. I'll fix it before I upload it. They're not going to hinder SN1 and E1 because they're not going to help favor that carbocation formation. And so one major thing about comparing these two solvents is how they interact with the nucleophile. Like I mentioned before, the polar protic solvent is going to surround that nucleophile, and it's going to hinder its nucleophilicity. And because small nucleophiles, you can think of them as like the negative charge is more tightly concentrated. And so there's going to be many more solvents surrounding it as compared to a much bigger molecule. So if you look at these, fluorine, that's going to be a very small molecule. Iodine, that's when you go down a group, so it has more electron shells. It's going to be a much bigger molecule. And so, so iodine is actually not going to be very affected by the solvent. So the way I've drawn it out like this, to compare and contrast the strengths of the different nucleophiles and different solvents, I've drawn iodine kind of in the same location, or in like, and because that's going to show like iodine, it's not like magically stronger in protic solvents. It's just that it's not very affected. And so because of that, the nucleophile strength isn't very effective. But something like fluorine is going to be highly affected. So in polar aprotic solvents, the nucleophile strength, it just basically follows the same trend as base strength. So fluorine is going to be your strongest base. It's the strongest nucleophile. Iodine is your weakest base. It's going to be the weakest nucleophile. But in polar protic solvents, because fluorine is so small, it's going to be more affected by the solvent. And so it's actually, we see the inverse. Fluorine is now the weakest nucleophile, and iodine is the strongest nucleophile. I just want to stress that iodine is not suddenly magically a much stronger nucleophile. It's still the same strength as before. It's just that relatively speaking, compared to the others, it's now stronger. And this is why SN2 reactions are limited in polar protic solvents, because all your nucleophiles are going to be much weaker. And if you remember, SN2 requires a very strong nucleophile. And that's why it's going to be hindered in polar protic solvents. One thing to keep in mind is that, just in case there's any confusion, solvents won't affect your leaving group strength. I just want to mention that because you can rank leaving groups. Your best leaving groups are going to be the weakest bases because those are the most stable anions. It's going to give you the most stable end product. And so you might think, oh, we see how these solvents can stabilize these anions. Maybe the solvent strength would affect leaving group strength. And it actually doesn't. I'm not going to go too much into why, but one reason is that when you're looking at these reactions, one thing that's going to affect like how favorable the reaction is the transition state. And because that transition state is going to be like so bulky, it's not really going to be affected by the solvent. So just like when you're doing problems, you don't need to consider the solvent when ranking leaving groups. Okay, another thing. So we've talked a lot about nucleophiles and bases. And you remember for SN2, that's going to require SN2, SN1 is going to require a nucleophile, and eliminations, that's going to require a base. So when you have cases where there's a molecule with either a very strong base, but a very strong nucleophile, but a weak base, like for example, this SH, H2S, and any halogens, that's a very clear-cut situation. You have a situation where it's something that's like a very strong base, but a weak nucleophile, like this butoxide you've seen a lot, and also NaH and KH. And just to be clear, the thing that's a base here is actually that H minus ion, that Na plus, and that K plus is just there to balance out the charge. The thing that's acting as base is that H minus. That's going to be a very strong base. And so when you have these situations, it's usually pretty clear cut. It's going to be substitution or elimination. There's a lot of cases where you'll actually be working with something that's both a pretty strong nucleophile and a pretty strong base. And you'll need to be able to look at all the other factors as well, but also be able to weigh between those two and try to determine if it's going to be a stronger nucleophile or a stronger base. And so because of that, we're going to look into some factors that increase nucleophile strength. So some main things like a charge. So nucleophile, if you remember, it's going to donate electrons. If it has more electron dense, so it has a negative charge, it's going to be easier for it to donate those electrons. Also, lack of electronegativity, that can be a bit counterintuitive for some people, but just remember, if it's going to hold on to those electrons very tightly, it's not going to donate them as easily. So less electronegative atoms are going to be better nucleophiles. Two major factors that definitely distinguish nucleophiles from bases is going to be steric hindrance and atom size. So for steric hindrance, bigger, bulkier atoms are not going to be as quick to donate their electrons. And so that steric hindrance is going to be a tertiary molecule. It's going to be kind of hindered by those substituents. It's going to be harder for it to attack. And so because of that, it's going to be a worse nucleophile. So if you see a lack of steric hindrance, that's going to increase nucleophile strength. Also large atom size. That's one reason why you see a lot of sulfur as like very good nucleophiles. This is because of two reasons. One main reason is that because it's got a very large size, it's very easy polarizable. It's very easy for it to donate those electrons and like attack, do nucleophile attack. Another thing is the thing we've mentioned before in protic solvents, that lack of solvation. So iodine, if it's in a protic solvent, it's not going to be very hindered by those. It's not going to be very solvated. And so because of that, its nucleophile strength is not going to be decreased. Just one thing to keep in mind, because just the stresses, even though nucleophile strength usually follows base strength, as you can see, these two differences, and that's because nucleophiles and basicity are two very different properties. Nucleophile strength is based on its kinetic property, so that means how fast reaction can occur. And for bases, that's where it's going to lie in the equilibrium. So you remember from acid-base chemistry, usually these reactions are both forward and backwards. So even if you can go through the reaction very quickly, if that reverse reaction also happens very quickly, you're not going to end up with a lot of end product. So essentially, a base is a measure of how stable your end product is going to be. If you have a very stable end product, that's going to be a very strong base. If that reaction happens very quickly, that's going to be a very strong nucleophile. And that's the difference between these two that you have to keep in mind. I'm not going to go too much into this table, but this table does appear in your textbook. I've written down the page number up here, page 427. And it basically just goes into a summary of everything we talked about like if you were trying to predict these substitution elimination reactions, you have to consider the substrate, the nucleophile strength, the base strength, and the solvent. I definitely don't recommend memorizing this table as much as I do understanding the concepts behind it, but this is definitely a very good way if like you're confused in some point or you just want to check your understanding to look at this table as a reference. One thing is that it only also goes into, this is a very simplified table, so it basically only goes into the major reactions expected. There's definitely a bunch of more complicated examples where you would see more than one product, which it doesn't really go into. Okay, does anyone have any questions before I go on? Because once again, there's a lot of concepts covered in these slides. Okay, if not, I'm just going to go on to the first practice. So rating the following reactions from fastest to slowest. So first we need to figure out what reaction is happening here. So we have this, this substrate and this Lewis space, and we need to figure out, and we also have this solvent, and we need to figure out what kind of reaction is going on. So does anyone remember what kind of solvent this HMPA is going to be? Is this polar protic or polar aprotic? Yeah.
Polar aprotic?
Exactly. This is polar aprotic. And so because of that, it's not going to have that, it's not going to surround this, if this is a nucleophile, it wasn't going to surround it. So looking at these halogens, are these going to be better nucleophiles or better bases, if you remember, these halogen ions? Just to reference the previous slide, halogens are always going to be, whenever you see a halogen, you can usually be pretty certain that's going to be a nucleophile and not a base, because they're strong nucleophiles but weak bases. So if you see a halogen, you can be pretty comfortable that's going to be a substitution reaction. And then looking at this substrate, just based on the substrate, if we were pretty sure this is a substitution, do you think this is going to be SN2 or SN1? Just looking at the substrate.
SN1?
Yeah, exactly, because it's tertiary. Okay, and so looking at these reactions, so we talked about how nucleophiles interact with solvents, right? So we said that this was a polar aprotic solvent, and we have these nucleophiles. So remember that reaction speed is based on nucleophile strength. So your strongest nucleophile is going to have the fastest reaction. So because of that, which reaction do you think is going to be the fastest here? Or a better question would be, which one is the strongest nucleophile? If this is polar aprotic. Yeah, F minus, because F minus here is your strongest base. And because this is polar aprotic, you're not going to have that weird solvation effect. So your strongest base is going to be your strongest nucleophile. If you have trouble remembering base strength too, also just remember that your strongest base is going to be the conjugate base of the weakest acid. So remember that HCl and HI, those are both very strong acids, if you remember from Gen Chem. And then HF, that's not a strong acid. So because of that, the conjugate base of HF is going to be a much stronger base than Cl minus and I minus. So that's one thing to keep in mind. So let's say, for example, we're going to replace this solvent, this polar aprotic solvent, with a polar protic solvent. So can anyone name a polar protic solvent? Just any solvent where there's an electronegative ion, like O or N connected to an H? Yeah, ethanol, that's a very good example. And H2O, that's also a very good example. Both of those have an O connected to an H. So let's say, for example, you had ethanol or water in these reactions. Which one would be your fastest reaction? Or which reaction has your strongest nucleophile? Yeah, this iodine molecule, that's your strongest nucleophile, so it would have the strongest reaction. And then this fluorine would have your slowest reaction. So yeah, you'll definitely see a lot of problems where you rank nucleophile strength in the course. They'll usually be more complicated than this, usually see bigger molecules, but this is a good thing to start thinking about. Okay, I think this is my last practice problem. Does it matter that, oh yeah, this should be an ion. This is a mistake. That's a good catch. I will fix that before I upload these slides. But yeah, this should definitely be an ion. Okay, this is my last practice problem. So I'll leave the floor to Sydney.
Hi guys, let me go ahead and share my screen. Alrighty, so we are going to do a couple of practice problems to review the concepts that Jennifer talked about. This is an example, again, of something you might expect to see during a Chem 3570 or OCSP practice problem or exam. We have our reagents, some are above the arrow, some below the arrow, and the question is asking us to predict the product. In order to do that, we have to think about what type of reaction is going to be taking place. So let's go ahead and analyze the reagents in this reaction one by one and think about what type of reaction could occur. So let's look at our substrate. First of all, what type of a substrate is our leaving group on? Secondary, thank you. Yes, so this is a secondary carbon. When the chlorine leaves, we will have a secondary carbocation. And that's kind of important because we aren't able to rule out any of our four major reactions here. Any one of them could take place. Alrighty, so we also need to look at the steric composition of the substrate. Does anyone see if we have any anti-periplanar hydrogens anywhere? This is an important question to consider because if we're wanting to know what about an E2 reaction, we would need to have an anti-periplanar hydrogen. And just as a reminder, that means that you have a hydrogen that is anti to your leaving group. So if this chlorine is on a wedge, then we would need to have another hydrogen that was on a dash in 3D orientation. So for example, this hydrogen is not anti to our leaving group. If you didn't know, for this molecule, we have a CH3 that's kind of on the end right here. And we're going to assume that because the leaving group is on a carbon that's this single bond right here, and these hydrogens are also connected to a carbon on that bond, we're going to assume that there's free rotation of this bond and that one of these hydrogens is going to be anti to our leaving group. So therefore, an E2 reaction is definitely possible. So I'll highlight these. Alrighty. And now let's take a look at this nucleophile or base, or I guess a broader term would be attacking molecule for now. Is this molecule a nucleophile? If you don't remember, this is tert-butyl, tert-butoxide rather, and I'm going to draw it out right here. You've definitely seen this before in lectures. This is a molecule that is a great base, but can't really act as a nucleophile because of all these methyl groups here. So strong base, but not a great nucleophile. Lastly, let's look at our solvent, which is written below the arrow. Does anyone remember what type of a solvent this is? So this might look familiar because it's the conjugate acid of our strong base right here. You should know that this is a non-polar protic solvent. So oftentimes when we see that OH, we assume that it's polar protic. This time it is non-polar protic. And non-polar protic solvents just have okay cation and anion solvation. So similar to a polar protic solvent, but definitely not a strong solvation. So I'll just write that up there. Alrighty, so we have analyzed kind of all the factors of our reaction. We've looked at our strong base, we've got a non-polar protic solvent this time, and we got a secondary substrate. Does anyone want to take a guess about what type of product we could expect to see? Well, in this case, whenever you see tert-butoxide, this base is very frequently featured in E2 reactions. Because if you remember, E2 reactions, they're concerted, and it's just a very great option to remove that hydrogen. Because tert-butoxide does not really act as a nucleophile, we shouldn't expect to really see any substitution reactions because substitution reactions need a nucleophile. So for this reason, our predicted product should be the E2 product. Just a reminder, the E2 product will feature a double bond between this carbon and this carbon, since this carbon is the one that has those anti-periplanar hydrogens. Definitely not between these two carbons, just because, as we talked about earlier, this hydrogen is not anti to our leaving group. Are there any questions about this example? Alrighty, let's go ahead and look at our last practice problem again then. This example, we have our, again, reagents written like this, and let's go through and take a peep at each of them. First of all, what type of carbon substrate are we looking at that has our leaving group? Alrighty, somebody says secondary. Wonderful. Thank you so much. Yep, this is a secondary carbon. So just like last time, we aren't able to rule out any of the 4 reactions because all 4 of them could take place on a secondary substrate. And then, just as we looked at last time, we want to see if there are any hydrogens that are anti-periplanar to our bromine. And once again, this 1 carbon down here has 3 hydrogens on it. This is a single bond right here. It's an alkane. We can assume free rotation and that one of these 3 hydrogens will be anti to our leaving group. So therefore, E2 reactions are a possibility. It's always important to do this check because if you have a substrate where there is no hydrogen that is anti-periplanar to your leaving group, then you aren't going to be able to have an E2 reaction. You can just cross that list off, that one off your list of possibilities. Okay, then we have our salt molecule. What type of an attacking molecule is our salt going to be? Well, the actual nucleophile is going to be our chlorine, and Cl- is indeed just a strong nucleophile because it is the conjugate of HCl, which is a strong acid. Therefore, Cl- is going to be an incredibly weak base. And lastly, what type of solvent do we have for this reaction? Somebody answered, it's polar protic. Thank you. So since we have a polar protic solvent, a larger halogen would be a stronger nucleophile. So if we had like an iodine or something, that would be a faster, better reaction, but fluorine is still pretty good. Alrighty, so based on the factors that we have here, what type of reaction would you expect to happen here? Alrighty, I see somebody is saying E2 and SN2, a lot of those. However, for E2, we aren't going to be able to have an E2 reaction because Cl- is a strong nucleophile, but it's not a base. So because Cl- cannot act as a base, and we need something that can act as a base for any sort of elimination reaction, we are not going to have any E1 or E2 reactions. We're only going to be able to look at substitution reactions because Cl- is only a nucleophile. And then somebody's asked if it would be an SN2 reaction, and the reason that we likely would not see an SN2 reaction is because H2O is a protic solvent, which provides solvation for both cations and anions. And this would prevent a strong negatively charged nucleophile like Cl- from moving very quickly. So it's going to be harder for Cl- to pull off a backside attack in a polar protic solvent. Let me rewrite that because I only wrote protic. It's going to be hard for an SN2 reaction to occur in a solvent like water. Now, if we had a polar aprotic solvent like DMSO, or as we saw in a previous example, HMPA, then that would be a good indicator that, yeah, maybe we are going to have an SN2 reaction going on, but not in this case. Ready, let me check for other factors. Okay, so in this reaction, as you might imagine, because I've kind of ruled almost everything else out, our predicted product is going to be SN1. Again, we're not going to have any elimination reactions because Cl- cannot act as a strong base. And we're not going to have an SN2 reaction because we have a polar protic solvent. And it's important to note that in this example, our SN1 product is actually going to have a methyl shift. We have, after the leaving group leaves, we're going to have a secondary carbocation, which is okay, but not super stable. So one of these methyl groups can hop on over onto this carbon, and we are going to have a tertiary carbocation right here. So our SN1 product will actually have a chlorine on this carbon. All right. So are there any questions about this practice problem before we move on? Feel free to raise your hands, unmute yourself, post in the chat. Somebody asked why you need a base for elimination, and the reason is that you're taking a hydrogen from your substrate in the E1 and E2 reactions. So we do have an anti-periplanar hydrogen. If we were looking at an E2 reaction, for an E1 reaction, the hydrogen does not necessarily have to be anti-periplanar. So suppose we did have a molecule that could act as a strong base, such as our tert butoxide from last time. In that case, we would be able to pull off an elimination reaction because we do have the hydrogens, and we would end up with a double bond. Sorry, it looks like there was a little bit of lag. Basically, if we had a strong base, we would be able to have an elimination product, which would feature a double bond between these two carbons. Are there any further questions? All righty. So you saw that Jennifer posted her own table. Well, not her own, but it was a table from the textbook that you guys are going to be using for 3570 with GANM this fall. I presented another table that's from a book called Organic Chemistry, the Second Language by Dr. David Klein. You've probably heard me reference that book a million times this summer. It is my very favorite organic chemistry resource, and I highly recommend. And this is, they have a version for Organic Chemistry 1 and a version for Organic Chemistry 2. This one is from Organic Chemistry 1. Just writing it up here in case anybody's interested. Basically, this table does kind of what Jennifer's table was doing earlier. I like it because it talks about the reagent, and then it gives you options for each mechanism that will occur based on the substrate that you're given. So for example, here's something we looked at earlier. Suppose you have tert butoxide and you have a secondary substrate you're going to be looking at an E2 reaction, which is what we talked about earlier. And they have really nice explanations here as well. Basically, when you have a reagent only as a base and not a nucleophile, you're only going to get elimination reactions. And then what we looked at today, or not today, but just before, if you have a nucleophile that only acts as a nucleophile, so for example, any halogens, I'll write that in there, like Cl-, and you have a secondary substrate. Here they say SN2, but they don't have a solvent as an option like we did. So for example, if we had a polar aprotic solvent, then we would be looking at an SN2 reaction. But because they're not assuming that you're having a solvent in your reaction, they have SN2. But for us, our answer was SN1. So I'll make a note of that. Does not include solvents. Regardless, I still thought this table was super helpful when I was studying organic chemistry. And just as Jennifer mentioned, you are not going to want to ideally memorize what's on here, but I think it's good to just kind of learn the logic behind each answer. And remember that things can be different depending on what solvents are included. So this is the last part of our lecture for today. It's kind of short just because we were reviewing what was taught earlier this week. Are there any questions that we can answer? Alrighty, I can stick around if there are any further questions. Everyone else is free to go. Have an awesome rest of your Wednesday, and we will see you guys on Friday.
Thank you.
Thank you.